Hey team, can everyone hear me? Great to be back for another week. How are we all? It's great to see so many of you once again, whether it's morning or evening. I've got a few from a few local people, a few Australian ones, a few New Zealand people this morning by the looks. Someone from Ballarat, wow, that's fantastic, which is where I live, so that's terrific to see. And it's not a particularly big place, so I love having folk that from nearby jumping on, so that's terrific. Oh, there's no shame in admitting you're from the US. Detonation, we love you. All right, let's make a bit of a start. So, what am I going to be talking about this week? It's all about microcontrollers, and in particular, what microcontrollers are in use by and will likely be used by Speeduino in the future. It's a big topic. I could talk for a long time about it. But we're going to try and compress as much as we can into a single hour and see how we go. As always, do feel free to fire off any questions as we go through. I suspect this one's going to be a fairly Q&A heavy type session, depending on how we go, because it's an interesting sort of topic. But let's dive into it and see where we get. All right, so I'm just going to start off with a brief sort of introduction around what I'm talking about, why these things exist, why they're different, and what the advantages and disadvantages are of one system over another. So what we see on screen here is a picture view of the classic Arduino Mega 2560. This is the one that has powered practically all of the Speeduino units that are out there today. It's fairly cheap, it's fairly simple to use, and has plenty of I/O for us to use. It's what's known as an AVR microcontroller, and that's the family of microcontroller. And what that means is, you might have heard, for example, of an x86 on your PC is that architecture, or an ARM architecture, which is in your phone or your tablet or something like that. This is a wholly separate architecture, again, known as AVR, and it's been around for a long time, and it was originally owned by a company called Atmel, which has since been sold to Microchip, and realistically it's a platform that is, whilst still very much active, and there's uses of it in thousands, millions of products out there, it's an architecture that's realistically not being developed any longer. They are 8-bit ECUs and MCUs, and I'm going to get to that in a minute about what that actually means. But in essence, they're a cheap, reliable, very well understood and very simple to use microcontroller that we're familiar with. The other two main ones that I'm going to be talking about today are Teensy boards, and in particular the Teensy 3.5. Now the Teensy is an alternative product made by a company called, or a site called PGRC, which is Paul Staffridgen. I'm sure I'm slaughtering his surname there, and apologies for that. But he develops this line of boards called the Teensy, and has done so for quite some time, which use a wholly separate chip, the MK64 or the MK66, depending on which version you happen to be going for. And those are an ARM chip, or an ARM Cortex chip. In this case, a Cortex M4 chip. And again, I'm going to talk to details in a little bit about what that actually means and why it makes it different. Can I turn my mic up a little bit? I can turn my mic up a little bit. Let's see if that's any better. You'll notice that it's a much physically smaller board. It has less I/O on it than the Mega, which is an advantage and a disadvantage. The size certainly helps, but it sometimes is a little bit of a disadvantage for some things as well. It does have further pins on the back that are a little bit more difficult to use. But we'll keep ticking on. The other thing you'll notice that on this board, despite being a bit smaller, it does also have an SD card slot built on. which is helpful. And there's a few other little peripherals on there that as well that I'm going to talk about in a little bit. Okay. I'm going to talk about two STM32 boards or chips. Now, I've mentioned STM32 previously, and they are another family of ARM chip. And they're manufactured by a different company. They work a little bit differently, but they have the same ARM cores in them as the Teensy. The way microcontroller families work is that a company will go out there and they will license a core from ARM, whether it be a Cortex M0, M1, M2, M3, M4, whatever it happens to be, and they will implement it in their own chip. And outside of that core, they will add different features to it. They can add different amounts of memory, they can add different amounts of peripherals in terms of timers, in terms of communication buses that are used, USB or CAN or LIN or anything like that, depending on what's available to them and what they are designing that chip for. And that's why, even though both the Teensy and the STM32, regardless of which chip we're using, are both ARM chips, they can be very, very different in terms of what they offer. And even saying STM32 is being a little bit too generic, because it's a massive family of different chips. So this one is an F407, and this board here is what's known as a blue pill board. These came out a few years ago, and are using a little STM32 F407 chip. As I said, they're quite small. They're, I think, even a little bit smaller than they would be, in fact, a little bit smaller than the Teensy. I have one of them somewhere around, but I haven't played with them an awful lot. And they're still available. They're very, very cheap to buy, in the orders of a couple of dollars, to get one of these working, or to get one of these in your hands. Speeduino will work on one of these. The reason they haven't been focused on is one around memory, and I'll touch upon it a little bit later. But I just wanted to show you a picture of one of these boards, and I'll show you one of these as well, which is, again, an STM32 board, so in the same family, but an F407 in this case, as opposed to the F407. This is a Cortex M4 as opposed to the blue pill, which is a Cortex M3, and is a much, much more powerful board. You'll note that there's a lot more I/O on it. We've got a battery for a real-time clock. We've got the SD card slot again, and a couple of different headers and things. So those are the main boards and the board families that I'm going to be talking about, simply because those are the major ones that I look at for Speeduino. Before I kick off anywhere else, I'm going to say a couple of different things that are very much my opinion only. They're not shared by necessarily everyone, and they're not even within the Speeduino development guys, I guess. But I think they're important points to make, and they primarily relate around user friendliness and how simple some of these boards are to use. One of the philosophies that I started with Speeduino was trying to make something that was accessible and as simple as possible. With the Arduino Mega, we get a lot for free, if that makes sense. And it's a lot that I guess users of the platform probably take for granted, which is fine. It's exactly how I want it to be. But in terms of how simple it is to use that board, how simple it is to upload firmware and things to those boards, it's very, very straightforward. I don't want to make a platform that's difficult for users to interact with and to work with. I think there are other systems out there that have gone down that path and have discovered that it is not a nice user experience, even if it might be a technically better experience in terms of raw hardware power and those sorts of things, but isn't necessarily as nice for the user. And that's a trap that I'm very nervous of falling into with anything Speeduino related. So all of my comments that I'll make today, and all of my personal opinions here, have that as a focus and have user simplicity as or one of the primary goals of the Speeduino project. Okay, so keeping all of that in mind, let's start to talk about what the advantages and disadvantages are of these. So the good old Arduino Mega is a 16 megahertz 8-bit chip, which is, if you, I guess, used to working with PCs or something like that, you look at 8-bit and you go, well, what does that mean as opposed to a 32-bit or a 64-bit machine? And 16 megahertz, it's relatively slow. Even in the modern microprocessor world, 16 megahertz is fairly slow. What it is, though, is enough. In terms of what Speeduino is using the microprocessor for, we're not pushing the limits of that 16 megahertz yet. We might get there one day in terms of features, but that 16 megahertz is really almost irrelevant at this point, because the way Speeduino has been written, that doesn't make too much impact, and we're not running into that limitation of CPU yet. Where we are hitting some limits on this chip, though, is around what's called timers. Timers in a microcontroller are little pieces of discrete hardware on these chips that we can use to time things accurately. And as you might expect, it's exactly what's being used for the ignition outputs, for the fuel outputs, and also some of the PWM outputs, so boost controls and idle controls and those sorts of things. Basically, all they are is a counter, as the name might suggest. We've been called timers, that simply counts up, and they will count up to a certain number and then go back to 0 and count up again. They can be configured to do different things, so they can count up to a number and then count back down again. But the way they're set up with Speeduino is just to count to a number, go back to 0 and count up to that number again. Sounds pretty simple, and realistically they are, but they're very, very useful because each count in that timer will take place at a very specific amount of time, and be very accurate in terms of how long there is between each tick on that counter. What we can use these to do is say, okay, if there is 4 microseconds or 2 microseconds happening between each of those ticks, we can say, okay, we want an ignition pulse to start in 30 milliseconds, for example, and run for 4 milliseconds. We can calculate how many ticks of that timer we're going to need before we start that ignition pulse, and then when we end that ignition pulse. So timers are very, very useful in that regard. Question, there is such a thing as virtual timers, kind of. You can use soft timers, as they're called, which uses the main clock of the CPU, but they're much more CPU intensive, and they're much less accurate as well. So that they're not really something that I would tend to use for anything like that. Volume's still a little bit low. Is anybody else getting volume low? Let me just move my mic around a little bit here. Hopefully that's a little bit better. We'll see how we go. So in terms of the limitations of the Arduino Mega, the timers are a much, much bigger factor than either it being 16 megahertz or only 8-bit. That's really what limits the Arduino Mega to only having 4 channels of fuel and 4 channels of ignition out. Although, of course, within the firmware, you can sort of shuffle those around, so you can have 8 and 0 or 6 and 3, as we have, for example, because we actually have 9 of those available. Still too low. Okay. Mixed comments on the mic. Okay. I might leave it as is for now, and see how we go. Okay, so to compare that to some of the other chips that we've talked about, in particular these two, there is, I can't even remember the number of timers on these chips. I should have looked it up before this session, but the short answer is that both the STM32 F407 and the Teensy boards have more timers than we're ever going to use. they have a huge number of them. Or maybe not more than we're ever going to use, but they have a more than sufficient to do 8 channels of fuel and 8 channels of ignition, for example. In my opinion, that's the single biggest factor for looking at other microcontrollers beyond the 2560. There's an awful lot of talk, and people get very excited about big numbers, and they say, okay, oh wow, this runs at, for example, the Teensy 3.5 runs at 120 megahertz. The STM32 F407 runs at 168 megahertz. The Teensy 3.6, which is mostly compatible with the 3.5, with a couple of different exceptions, runs at 180 megahertz. And if we jump up to the Teensy 4.1, which I actually have some test code running on, and is also largely pin compatible with the Teensy 3.5, that's running at 600 megahertz. And these numbers look fantastic, particularly compared to a little number like 16 megahertz. But in reality, they make almost no difference to Speeduino. The analogy I tend to use is everybody loves bigger numbers, but if you put a microcontroller in a toaster to control your heat, it doesn't matter whether that's 16 megahertz or 600 megahertz. The outcome is still toast. And the toast will be the same regardless of what speed your microcontroller is running at. It's similar, although more complex, with Speeduino. You only need a microcontroller that is fast enough to do what you want to do. And that's what we have for the most part with the 2560, with the limitations around timers. Probably the next biggest consideration with these chips is the amount of memory on board. And there's 3 kinds of memory that we really need to worry about when we're talking about microcontrollers. There's flash memory, which is where we're storing the program, so where we store the firmware on these chips. There's actual RAM usage, so much like we have RAM in our PCs, these chips have RAM on them as well. And there's also non-volatile memory, or typically what's known as EEPROM memory. It doesn't always have to be EEPROM technology, but it often gets referred to as EEPROM regardless. And this is where some of the user friendliness that I was talking about comes in. The Arduino Mega and the Teensy both have a certain amount of memory that's on the chips themselves for storing things. And in the case of Speeduino, that use is for storing the tune. The tune we have within Tuner Studio and the configuration that we set up has to be stored somewhere. And typically in a microcontroller, it can't be stored in the same place as a program. There's and I really won't get into details about it, but there's a school of thought around microcontrollers called the Harvard architecture, which separates these 3 chunks of memory and says that they can't be used, even though they're all memory, one of them can't be used for the function of another. So we can't use the space that's on these chips that's reserved for the program or for the firmware. We can't reuse that memory for the tune. Likewise, we can't reuse it as RAM on the chip. So there's very good reasons for doing that, which are more complex than what I want to get into today. But the short of it is that we do have some storage space for our tune on the Mega and on the Teensy. On the STM32 we don't. There is no runtime writable non-volatile memory on these chips, which means there's nowhere on the chip itself that we can save a tune to. Those of you with sharp eyes will note that we also have this chip on these blackboards though, called Flash. And this is an external storage chip that can be used. Now, there are a couple of considerations with doing it in terms of how we talk to that chip. And if we have a different board, a different STM32 F407, and there are some simpler boards out there that don't have this on board and simply won't ever work with Speeduino because we have nowhere to store the tune on them. You can load the firmware to it, you can fire up Tuner Studio, you can change different options in the tune, but those options will only ever be getting stored into the temporary RAM on that chip. They won't be going back and actually getting stored anywhere. Question there, how do you assign outputs to do V8 sequential fuel. You mentioned it was a case of assigning outputs after showing the options in the code. Yep, okay. It's a little bit complex, but it's probably something that I'm going to get to in a minute, because I will flick over to the code side of things shortly. Remind me if I forget to come back to that one. Okay, so in addition to the number of timers that they give us and the amount of onboard storage, realistically the biggest difference that we have between all of these boards is the peripherals that they add on to them. Now timers are one of those that we spoke about, but the more modern chips, the F407 and the Teensy, the Teensy 3.5 that we're using here, have things like CAN communications built onto them as well. And that's pretty useful, and that's certainly the direction that Speeduino will be going, to add features like that. You still need to add, in terms of CAN, you still need to add what's called a transceiver to be able to allow that CAN bus to talk to an external system. But it's certainly well on its way to having things like that built on. In my opinion, the biggest advantages of a different chip architecture are the increased timers, the additional built-in peripherals such as CAN, and that's almost it. There's not very much else that you really get from these chips that's an advantage. The clock speed is nice, it means you can be lazy with your code, but the 2560 will always be a supported platform for Speeduino. It's never going to be removed from support. There will be some cases where there are features that I can't add on to these due to hardware limitations, but for everything else it will be supported on the 2560, and that means that I have to keep working within a 16 megahertz clock speed, and that just means I have to be careful with my code still, and I'm not going to write lazy code just because I'm now working on a different chip that's got 120 or 168 or whatever megahertz to play with, because it doesn't make sense, and these will always be a very, very rock solid and reliable unit to keep programming for. Alright, so most of what I've spoken about here is what the limitations are of the Mega 2560 and what the advantages of some of these newer chips are. But, and this is a pretty big but, they come with disadvantages as well. And in some cases they might be disadvantages that you don't care about. In a lot of cases though, or in some cases, they're things that I consider to be fairly important to most of the Speeduino user base. And that's what I'm going to talk about next, because it's not always as straightforward as just saying, hey, we've got a nice fast chip now, let's start using that. If time permits, I might talk about what the coding differences are between these. But that's probably something I'll leave to the end a little bit and see how we go for time. By far, the biggest and first consideration when using these chips, particularly from a hardware design point of view, is that these don't operate at 5 volts. The good old 2560 functions at 5 volts, which makes things really, really simple, because much of the automotive sensor environment is geared around 5 volt sensors. And that makes them a lot simpler to use. It's also the same voltage that we have for USB, which makes things a little bit simpler there as well. Let me just catch up with comments. Comment from Ruba, there are 8 functional timers in Mega from memory. Sorry, there are 9 functional timers in memory. There's actually more than that. 9 are what we have left over when we take other things out of the equation that are left over for fuel and ignition. So by the time we take out boost, and by the time we take out idle control, and we take out a system timer and all these sorts of things, there are 9 timers left for fuel and ignition. Ruben, I always plan to have these sessions run for about an hour. They tend to go over by 10 or 15 minutes, but we'll see how we go for today. Okay, so these chips here all operate at 3.3 volt, which is fairly common for modern microprocessors. And really they have a focus on lower power. It's not something that's a consideration for Speeduino because we have a constant source of really strong power, but the focus of modern microcontrollers is going into environments where they're often battery powered, and low power is much more desirable than it is in an ECU. And that's why a lot of these now work at 3.3 volts or even 1.8 volts is now becoming somewhat common. And it's the same for the STM32. And what this means in hardware is that we have to take a couple of different things into consideration. So I'm going to jump back into KiCad here. KiCad's the software, or sorry, the hardware design tool that I've been using for all my new boards and then I've shown off the last couple of weeks. And I'm going to give you an example of where we have to take this into account. And there's really two areas. There's inputs and there's outputs. Any of the inputs that the Teensy board takes need to be compatible with that 3.3 volt signal. Now, for various reasons, the Teensy 3.5 is actually 5 volt tolerant, which means it can accept a 5 volt signal without being damaged, but it can't take or can't read an analog signal, for example, up to 5 volts. It can only read an analog signal up to 3.3 volts. And the same goes for any of the STM32 chips. So we need to add a little bit of circuitry like this in. If we have, for example, any of our sensors like a map sensor, which is powered by 5 volt and spits out a 5 volt or a 0 to 5 volt signal, same with our baro sensor, same with an O2 sensor, all these sorts of things, we need to somehow turn that 5 volt signal into 3.3 volts. This is not a difficult thing to do, but it's something that has to be considered on the board, and it's something that we have to take into account when we're doing the design. Now in this case we use a fairly simple voltage divider between two resistors, a 180k and a 330k, which if you do your Ohm's law calculations on that, you'll discover turns 5 volts into 3.3 or very close to. We could feed that signal directly into an analog port on one of these boards, and it would kind of work, but the amount of current that we would have coming through here because of the resistor values would be exceptionally low, and we can use lower value resistors, but we're still affecting the amount of current that we would have hitting the analog port or analog pin on the MCU. So we need to run it through what's called an op-amp, which is increasing that current whilst leaving the voltage unchanged. Now this setup here is a quad op-amp that we use, or that I'm using. So it's got 4 op-amps built into it. There's actually this particular board. This is from the schematic of the drop bear board. This particular board has 2 of these op-amps on it. One is here, one is on another sheet. But essentially all they're doing is turning all our 5 volt signals, so our baro signal, our map signal, our O2 signal, and our TPS signal, which are all traditionally 5 volt sensors in an automotive environment, to give us our nice 0 to 3.3 volt signal. This is not a difficult thing to do, but it's a consideration because once we start to get into these more complex designs, all of these ICs take up space, and all of the resistors and everything take up space on the board. And they also start adding to cost as well. It's not massive, but with the goals of simplicity and low cost in mind, they are certainly a consideration. Question here: if we have to add additional hardware to work with these microcontrollers, why not add some hardware to the 2560 for additional features similar to what VEM's ECU with the Mega 128? Interesting idea. So it's a different way of looking at it. In my opinion, if we're going to add hardware anyway, we might as well use a newer chip to do it with, because we do get the things like the onboard SD, the CAN bus built in, all those sorts of things. But it's a very valid question about why we couldn't add, for example, an external timer unit, which you can get, onto the 2560 and use something like that instead. That is certainly an option. It's not something I've ever coded, not like I've ever looked at doing the coding support for. It wouldn't be too difficult to add, but I guess it's a question of, given the hardware isn't out there already on those boards, you would have to have a specific board to add that anyway. You know, if it was built onto the Arduino Mega board itself, then that would be different. But if you're already having to add specific hardware onto your Speeduino board to handle that, why not just cater to a different microcontroller in the first place? Again, it's all just opinions, and it's a very valid question about why that's not an option, and it probably is. Okay, so that's how we handle analog inputs on one of these. The other and important consideration is how we use outputs. So the outputs on these pins is always going to be, instead of 5 volts, 3.3 volts. That, for the most part, is okay, depending on what we want to do. But in some cases, it provides, or it proves to be a little bit of a limitation. I'm going to jump in the output section for you here and give a perfect example of where it's a problem. So these are the generic output drivers on the early Alpha 2 drop bear units. The Alpha 3 and 4, the Alpha 4 boards and later have changed this a little bit. But this here, the VNLD 5090 chip, is simply a dual MOSFET. So it's a driver, it has 2 MOSFET chips in it, a little bit of other protection and that sort of thing as well. Oh, really good question. I did say this before, and I was talking about something else. I forgot to mention it. Why not the Arduino Duo? Okay, the Arduino Duo I looked at very early on when I was considering other microprocessors to use. It's a massive pain of a chip. It's really very, very limited. It has no onboard storage, so again, you've got to be adding a flash chip to it to actually store your tune. It has very limited timers. Its timer architecture is not that much different from the 2560. So it doesn't actually get you anything. It gets you a higher clock speed, it gets you an ARM chip, but in terms of its capabilities with the Speeduino firmware, it would actually be less, in my opinion, than what we get with the 2560. So it's a step backwards, at least in my thinking, compared to what we already have today. It's a very, very limited chip, unfortunately. It's an odd choice. It was one of the first Atmel ARM chips, and in my opinion was a bit of a failure, if I'm honest. I don't think that was a particularly useful chip at all, but not for Speeduino in any case. Okay, getting back to our MOSFETs here. For those who know a little bit about electronics, the way a MOSFET works is by having a gate, which is your input, a source of power, and a drain. When the input goes high, it allows current to flow from the source to the drain, or vice versa, depending on how you want to look at electronics. And we use this for controlling various loads off board. So, you know, this is a spare output here. Here's one for fan and boost using exactly the same chip. We can control a boost solenoid with this. We can control a fan relay, those sorts of things that we can't do directly off a pin. The way a MOSFET works is it will trip, or it will switch between on and off based on the voltage at its input. And that's typically what's referred to as a gate threshold voltage. Lots of MOSFETs out there will have a gate threshold voltage somewhere around 2 volts, but some of the higher capacity ones, so the ones that can flow more current, which this VNLD 5090 is a perfect example of. And thank you so much for the donation there, Raphael. I appreciate that. They actually require a voltage to trip that gate that's above 3.3 volts, which means that if we had to drive them with directly from the pin of a Teensy or an STM32, it won't completely trip that gate, and it will only partially open. This is what I set up on the Alpha 2. I think Alpha 3 of the drop bears. I can't quite remember when I changed it, to do some testing on, because the threshold voltage, I think or the full threshold voltage on these chips was 3.5 volts, which is very, very close to 3.3 volt. So I wanted to try it and see how close it was. The answer is not close enough. So you get an issue here where you're trying to drive a load with 3.3 volts onto the gate of these MOSFETs, and the output is either limited in terms of current, so you might only be able to get 1 amp output when you should be able to get 5 amps output, or that output becomes unreliable in that it will flick on and off very, very quickly. So it's not workable in this state. The later drop bear units use a different dual MOSFET in the same family as this one, that has a 2 volt gate threshold. So very much easier to drive off these lower voltage microcontrollers, and that makes things a little bit simpler. There are other options, of course. You can use a pre-gate driver, is what they're called, which will turn your 3.3 volts into 5 volts. It's basically just a fancy op-amp like we looked at before, but going in the opposite direction. And that will drive the voltage and the current to the gate. That was another option. If I wanted to keep the VNLD 5090 chips on this board, I could have added one of those level translators in, or pre-gate drivers in, and that would have allowed me to keep using them. But in my case, it was just as easy to switch to a driver that was tolerant of, or could switch at 2 volts or 3.3 volts, and not have to add anything else onto the board. Oh, how good's this? My little helper has just delivered me a coffee again. How good's that for a Sunday morning? Thank you, darling. All right. So those are two of the main considerations in terms of voltages here. What chip did I go with? Okay, this is the schematic for the drop bear boards, which is still in alpha. This is a board that uses the Teensy 3.5. And that's probably where I'm going to get to next, is the question of why did I go with Teensy over STM32? Because a lot of the people are out there that are working on STM32, and now for the most part in the firmware it is supported pretty well. And why I went with Teensy over that one. And there's a few different reasons, and they all realistically come back to what I was talking about at the start in terms of user friendliness. The Teensy boards are designed to be very, very user friendly. You can plug them in on Mac and Windows and Linux, and they operate with no drivers. We can upload a firmware directly to them. So one of the things I think a lot of people take for granted is when we plug in our Arduino Megas and we load up Speeduino, and again, the entire purpose of Speeduino was to make life simpler for people, to make it a nice user experience for how we get updated firmware versions onto these boards. All we do is we plug in our USB, we fire up Speeduino, and provided that Tuner Studio is not running in the background, we simply hit upload and it will upload the firmware to the board. That's all we have to do. It doesn't wipe the internal memory at all. It doesn't require us to put any jumpers on the board or anything like that. It doesn't require us to manually press a reset button at a certain time. It doesn't require us to put the chip into a certain mode in order to accept new code or anything like that. It's a very, very simple and very nice user experience, in my opinion. And a lot of people, I guess, take that for granted because of how simple that is. That's not the case with all microcontrollers. In fact, that's very rare, and it's not what you get with a typical microcontroller experience. It is, though, an experience that's been largely replicated with the Teensy. Paul, who runs Teensy, produces some amazing high-quality libraries to go with it. And in terms of the bootloader that he's written for it, it operates in a very, very user-friendly way, much like the traditional Arduinos, in that he provides a nice firmware loader package that we can use. And this is answering the question here about will Speeduino support Teensy and STM32 boards. It will unquestionably support Teensy once this stuff comes out. I will drop a new version of Teensy, Speeduino, which I've been tinkering with in the background, that works with Teensy. Because all of these things are nicely supplied and because it's a nice user experience, I can work that into Speeduino without too much worry. From that perspective, I really like the way that Teensy works. Again, it's got the onboard storage similar to the 2560, so we can store our tune on board without having to have any external storage or anything like that. We get the nice experience of just plugging a board in without having to worry about drivers and those sorts of things, and we can connect to it very, very simply, and we can upload our firmware to it very, very simply. Comment, there's the HID USB boost loader that works the same as that. I disagree. It works, it in theory works the same, and its idea is that it works the same. I've always found it to be difficult. I'm not sure if it's ever has been ported to the F407 boards. That's a very good question. I don't know the answers to it. So I guess that's something I could look at, but my preference, and for those reasons that I've talked about in terms of user experience, I've elected to go with the Teensy. Maybe that might change in the future. Like I said, that there is actually another version of the drop bear board that I've made that uses this same STM32 Black board, and that's what this board is referred to, by the way, as it's the F407 Black, because they're all black. There are some considerations here. It's a much physically larger board, but it does have more on board itself, so it kind of cancels each other out. I won't say that there will never be a version of it that uses something like this, but for the moment, the Teensy board is the one I'm focusing on. And it does mean that there are advantages, like in the future, you can unplug the 3.5, the Teensy 3.5, plug in a Teensy 4.1, which again is mostly pin compatible, not 100%, but mostly pin compatible. Load the firmware, and then away you go. You've got a 600 megahertz ECU. That's very theoretical. It's not where I'm targeting things today, but it is something that's worth considering. All right, how are we going for time? Okay, 15 minutes left. That is also, by the way, a lot of people ask me why I stick to the idea of using external plug-in boards rather than embedding the chip on board. There's a couple of reasons. I really love the idea that you can just unplug one chip, plug another one in, and perform an upgrade on your board. I also think that given the audience of Speeduino, and it's mostly DIY, it's much easier to if you make a bit of a boo-boo and short something out that you shouldn't have, or wire something up in a way that you really shouldn't have, and you end up killing a pin, or maybe even killing the entire chip itself, it's so much simpler to be able to buy another $10 or $15 board and simply plug that in, rather than either throwing away the whole lot because you've burned out a processor that's on the board itself, or having to send it back for repairs if they're possible. The blue pill is certainly an attractive board. That's an interesting comment. Now, the development around blue pill, which is this little STM board that I mentioned at the start, that got dropped pretty early on, and it does support. There was support written originally. This was the first STM32 board that was really targeted. These were dropped because they only had 64K of flash space, which at the time was very, very borderline for fitting the Speeduino firmware into, and now it simply won't fit at all with things that have been added to the firmware. It just won't fit in 64K. However, most of the new blue pills that seem to be hitting the market now have 128K of flash, which will work fine, and we're not. I think the firmware on these is only coming out about 70K at the moment. So we've got plenty of headroom there. That's something interesting that I haven't really gone back and revisited, because we sort of moved in different directions, particularly with the black boards and those sorts of things. But yeah, look, these things are stupidly cheap. I think they're about $3 or $4 each or something. They're crazy cheap. They're a little bit more limited, again, in terms of storage on them, in terms of there's not an SD card, I don't think, on the back of these or anything. But it might be worth revisiting now that the 128K variants of these have started becoming very, very common. I don't have one. The only Blue Pill board I have around is the 64K one. But it might be worth looking at those again. A couple of comments there about Blue Pill versus Black Pill. That's fine. Off topic, would we be able to make a limp home mode that ignores sensors like temp and TPS and O2 and just runs a real basic limp tune? Yeah, that is, I mean, that's kind of what we already have today, believe it or not. It just sort of works in the background and you don't see it much. If I have improved it in the development firmware, and we'll do so a little bit more. I realize I'm shooting off on a tangent here, but somebody actually made a comment last week that they liked the tangents. If a sensor goes open, so it either drops to 0 volts or 5 volts, depending on the type of sensor, that will get picked up by the error checking system in Speeduino, and it will flag that there's an error condition, and it actually it will set that sensor value to a default. And I'll show you, just jump on the Speeduino wiki for a moment. Yeah, so perfect question here by Monches. Apologies if I'm slaughtering that name there. So for a 4-cylinder Miata, is there any upside to Teensy versus the Mega? Sounds like this is for more cylinders. Yes, exactly right. There is absolutely nothing that these other microcontrollers, be they STM32 or Teensy, gives you on a 4-cylinder board today. In the future, I guess the only ones that might become a factor is that you would be SD card logging and potentially CAN bus support. Now, the early Miatas don't have CAN bus anyway, so that may or may not be a big deal to you. SD card logging is something that I'm working on at the moment, tinkering away in the background. It's not a high priority for me. I've got a few other higher priorities to work through. When that comes about, though, it will be something that you can add on externally as well. So it won't be there by default in anything that uses a Mega, but will be able to be added. But other than that, there is absolutely no benefit to moving to one of those newer microcontrollers, in my opinion. This is the error page on the wiki, and it pops up a table for an error number. So this is, if you see an error number appearing in your in Tuner Studio or in your log, you can refer to this table to look up what that error number is and what it means. For example, if you see error number 4 come up, it means that the coolant sensor is shorted to 5 volt. So it's just a maximum reading. In addition to flagging this error, it will set the default value of the coolant reading to 40 degrees C. Now 40 degrees C is a somewhat safe value. It's going to, in most tunes, but in most setups it will richen the fuel up because it will go into a warm-up mode based on it being quite cold. And that will then operate as a safe value until that sensor can be fixed. So whether we want to call that limp home or whether we want to call it anything else, there is this system in place already to do that. Now, what I'm working on at the moment is enhancing this a little bit, improving the number of errors that are being, or that can be tracked, and also allowing these values to be set in the tune rather than just having default values. All right, just looking through comments here to see if there's anything I've missed. Yeah, cool. Okay, I think I've caught up on most of those. A couple of questions there from David around the op amps, and yeah, some of the earlier Teensy adapter boards had rail-to-rail systems that were incorrectly clipping, I should say, and caused a few problems. That's been addressed on newer ones. Cool. Okay. The final thing I really wanted to touch on, just keeping an eye on time here, I guess was around some of the coding and what this means and how we handle the different microcontrollers in code. I can pull up the code here, and this is our master globals file. Now, the idea in how I wrote the multi-architecture support into Speeduino's firmware was that there would be a little bit of code in globals.h that would set a few things up for each individual architecture with the Arduino Mega or Teensy or STM32, and that would handle setting and initializing some of these things up, but that all of the other board or architecture specific code would go into these files here. So board AVR 2560, which is for the Mega, a couple of different ones for the STM32s, depending on which core you're using, and the Teensy 35 and Teensy 40s. For the most part, that works well. There is a couple of other areas around in the code where there is architecture specific code. I try to remove that wherever I can, but in some places it's not possible. But if you jump into this globals file, you will see that for each of these, for each family or for each architecture, we define a default number of ignition channels and a default number of injector channels. In the case of the Arduino Mega, the 2560, that's 4 injector channels and 5 ignition channels. Most of these boards only have 4 ignition channel outputs, but they do still have a definition or the ability to do 5 channels as they're compiled. How this relates to what's happening on a given board or an actual Speeduino board itself is all in this init file. In this file here, it's a big file, bigger than it should be realistically, but if we scroll down we get to a pin mapping section, cool, which is this bit here. Okay, set pin mapping. For every board ID that we have, and the boards here in this case are a Speeduino V0.3 or 0.4 or a Miata plug and play or a drop bear or a UA4C or anything like that. This is what we select in Tuner Studio when we select our board. It defines which pins on those board are used for each individual function. Now, for some of these, you'll note that it has a standard pin mapping and a separate section for a Teensy. So this is if we were to plug a Teensy adapter board into a V0.3 shield, which is this case here, case 2. These are the pin mappings that you'd get for your standard Arduino, which is considered the default case. But if you've got a Teensy 35 adapter board plugged in, you would get, or you would change the pin maps to be these ones. If someone were to create an STM32 adapter board that plugs into the V0.3, we could add another section in here to handle the pin mappings for that as well. Is it possible to run two boards to 2 separate tunes, or is that necessary? Is that for trying to get, and that's a question from Mike Kane there. Mike, is that a question around trying to add more cylinders of support? If so, the answer is yes. There are a couple of crazy people out there who've used 2 Speeduinos to run V12 engines, for example. There's 2 V12 engines now, I think, running. It gets a little bit messy because you have to keep those tunes in sync, because even though they will be controlling different cylinders, you still need the tunes to be roughly the same. It can get a little bit messy, but it certainly is possible. Obviously, it's a fairly extreme way to do it, but it is possible. David, I'll shoot you a message or grab you on Slack after this one to talk about those adapter boards if you want. About noise resistance of 3.3 volt chips. That's an interesting question. because you're operating at a lower voltage, you've got less tolerance for electrical noise before it causes issues. I haven't seen this to be a huge problem. I guess a lot of it comes down to things like your power supply design or your power regulator design, and how good that is. I don't know. It's that there's a couple of different considerations here depending on what you're doing with your ECU, how you're housing it. If you're putting it into a metal case for electrical noise shielding, whether you're mounting it under or in the engine bay or near the engine bay versus in the passenger footwell or something like that. It's not. I haven't found it to be a huge problem, Chris and Ed Venus. I don't know. I don't have much more I can really add to it, simply because I haven't found it to be a big problem on these chips at all, in terms of trying to control the noise on them. It is a consideration, but it's not something I've had a problem with at all. Michael Dunning, I'm struggling to find out how many inputs are supported on the V0.3 and 0.4 boards. Will the wiring driving boards be available on the wiki be updated soon? I had thought what was on the wiki was correct, but maybe not. We can have a quick look though. The pinouts that are mentioned here pretty much should cover everything I thought, Michael. Maybe I'm missing something. There's maybe some more comments I can add around the proto area if that's what you're talking about in terms of your I/O. I don't know, shoot me a message if there's any specific details you want and we can add in. Ashley, I'll shoot you a message after this one. I'll let you know what's going on with that. That has been sent though. V0.3 in particular, Michael. Let's have a look. Yeah, okay, so that there's probably a few details I can add to the wiki page there, Michael. I'll take a look at that one afterward. Okay, so a question around, we need fuel pressure and oil pressure as default map pins. Yes, they will get added as defaults. For the most part, though, the feature that's getting added around fuel and oil pressure sensing is something that you'll select a pin for, because it will depend very much on which board you're running, and which analog or spare analog pins that you've got broken out. There will be default pins for those though as well. The old question around an FPGA instead of the MCU. Typically, if you're going to do an ECU with an FPGA, and I won't go into the details of what an FPGA is, for those who know, you'll understand the answer. For those who don't know, the answer will probably tell you why I'm probably not going to look at it. Generally, if you want to use an ECU with an FPGA, you would have a regular microcontroller and an FPGA as well. And typically the FPGA would be doing things like the decoding of the trigger pattern, and potentially the handling of the timing as well. But usually it's just the decoding of the trigger patterns and those sorts of things. I've looked at them. I don't think they're currently the best way to do it, not for Speeduino at least. They have a couple of distinct disadvantages in that they are a bit of a pain to work with in terms of setting code up for them and things. Not impossible, but it's got some quirks to it. And also in terms of how we go about doing updates to the FPGA itself. So you then not only have a consideration of updating the microcontroller, but then also updating the FPGA and how you do that in a user-friendly way. There's a lot of complexities that it gets into, none of which I think are particularly easy problems to solve from a user experience point of view. But the bigger thing is I just don't think they're necessary. I think there was a sort of intermediate period, maybe 10 years ago, where We didn't have the cheap high-speed microcontrollers that we do today. A couple of the ones I've talked about today being perfect examples. And where FPGAs then, for much more advanced ECUs, started to become something that you had to have, because the microcontrollers that we had simply didn't have enough power to be able to do some of the more complex things that those ECUs do. And so they had to turn to FPGAs. These days, I don't think they're necessary. That's very much my own opinion, and many people will disagree with me there. But I think in the days where we've got a cheap, easy 170 odd megahertz microcontroller that we can pluck out, there's not that much benefit to doing things in an FPGA. We get support for 0.1 timing increments in the future. That's an interesting one, possibly. It's a question of diminishing returns, right? And also a question of how much you actually get in terms of those 0.1 timing. It all comes back to, and I spoke about this on a previous stream, the internal math code has to be updated in Speeduino first to handle increments of a degree. I need to go through and do that work before we can make the front end tunable at 0.1 degree increments, or even less. It's a lot of work. It's something that is very much on my to-do list at some point, but it's a massive piece of code to write is all. So it's something I haven't tackled to this point yet. But yeah, but Mitch, it's on the radar. Cool. So I think I've caught up with most of the questions there. In terms of the actual microcontrollers that this session was about, I've covered off most of what I wanted to talk about, I think. Let me have a look. I actually made a list for this one. Normally I just play it by ear and talk about what I'm going to talk about, but I actually made a list for what I wanted to talk about on this one. And I think I have covered off most of the things there for it. If you do have any questions, by all means fire them up now while I'm still here, particularly if they are about either of these microcontrollers. But sort of otherwise, we're probably getting to the end of this week's session. Hopefully that's given you a good overview of the different considerations that are there for the different microcontrollers. The biggest thing I can say is that this is obviously something that's happening within Speeduino. The Mega platform will not be abandoned. I've sort of said that a couple of times, but I really do want to reiterate that. But for anyone out there who's looking at different architectures, be they STM32 or something weird like that, I looked pretty seriously at the SAM-C and SAM-D chips for a while and wrote some basic code around those. If you're looking at things like that, the biggest thing I can say is consider the user experience. Consider what it's going to be like for users to upgrade firmware on these units. Is it going to wipe the microcontroller so they have to reload the tune? And that's a very common thing in the microcontroller world. Is it going to require them to change boot jumpers or anything like that? Consider the user experience is my biggest advice that I can give when considering different architectures here. And that said, that by no means does that restrict out people who want to do things in a bit of a DIY way. You know, that will always be available to people who want to tinker, who are happy mucking around with these sorts of things that are a little bit more in depth. But don't be offended if I tell you that it might not be the direction that the main Speeduino project wants to go, because there are other considerations than just the tinkerer and just the person who is happy getting their hands dirty in the code and the electronics, because that's not the majority of Speeduino users. Vida, the comment here, you should consider to move the voltage divider after the op amps. Man, we could debate this for hours. I've got a pretty strong opinion that they should be before the op amp, but we can take that offline. I had that discussion with Parsi again the other day. So this is, sorry guys, getting back to a conversation that we had on Slack, but it's around There's op-amp circuit again, and whether we put the voltage divider, so these two resistance, before the op-amp or after the op-amp, there's pretty good arguments for both cases. My opinion is that if you put them after the op-amp, you have to put another op-amp in to balance that, or to make sure you've still got required current. Yeah, it's a pretty long debate, that one. We could go around in circles on that for a while. Andy Stevenson, you mentioned a 2-volt threshold. Thanks so much for the donation, Mitch. Really appreciate that. Mentioned a 2-volt threshold MOSFET for Teensy output. Which one do you use? Oh, that's a really good question. What is it? It's in. I can't remember off the top of my head, I'm afraid, Andy. It's another one that's in the same family from ST as the VNLD 5090. I don't have that schematic handy. It's on my other PC, I'm afraid. If you look up, if you look up the family for the VNLD 5090 though, you'll be able to see all the other MOSFET drivers in that family. There's another one there that works with 2 volts. You'll find it. It is lower current, as in it can't supply as much current as the 5090, but it's sufficient for what I'm using them for. So yeah, if you go through this family on the ST site, you'll find which one it is. I just can't remember off the top of my head. Could I run a session on EFI hardware basics? So a lot of inputs on these boards, and what do you need them for? So Chris, that's just in terms of how we hook up sensors, how we hook up outputs and those sorts of things. Yeah, I could totally run a session on that. That'd be fine. I'm always looking for what to do next. In terms of the comment about the Speeduino, I'm actually slowly but surely getting my ducks in a row to do one of these live streams on where Speeduino is at, how it works, what it does, what the details of it are. So keep your eyes peeled for that. It will be coming though. Michael Dunning, with drop Bebby SMD only? Yes, primarily SMD. There are some through-hole components on it for higher current components, but yeah, for the most part it is SMD. It's pretty much impossible these days to do a board of complexity like the drop bear without going surface mount, I'm afraid. It's just the realities of the complexity there. Has there been any thought to doing some abstraction from the Arduino dev environment in case a user wants to compile on another unsupported architecture? The development work on Speeduino these days isn't in the Arduino IDE, so it's not limited by the IDE or anything crazy like that. It does rely upon some fairly standardized Arduino libraries though. Now that doesn't mean they have to be Arduino code, there just has to be equivalents of those libraries available, and that's in terms of things like serial and that sort of thing. If you're looking at doing another architecture, see if it's something for which those frameworks already exist on Platform IO. And so this is addressing a question from Keith Rolstad here. Look to see if those platforms already exist on Platform IO, because that will save you a lot of time. Otherwise, the best advice I could give is simply to re-implement the required libraries, because there's not that much there. It's sort of serial libraries, an EEPROM library, a couple of basic input-output functions, and that's almost it that still requires the Arduino framework, for lack of a better word. It's really not that hard. So I probably won't move away from using those specific abstractions, but if you want to do another architecture that's completely unsupported, even on Platform IO, and they don't have a framework for it or anything, it's not that hard to re-implement those few libraries, simply because those are good ones to have. They're really useful in terms of what Speeduino needs to do, so they're the kind of things you would need to re-implement an abstraction layer for anyway, so why not use the same naming scheme and that sort of thing as what we have on Arduino. I guess that's my thinking on it, Keith. I don't think it holds us back in any way using that framework, though. Any thoughts on using ESP32 or SAMD? SAMD I did look at, SAMC and SAMD, and in fact SAME as well I think I looked at the time. It's going back a little way now, to the point where, oh, it might not be on this PC, but there was a board file written for them and an abstraction layer and everything written for those systems. The SAMD I felt was too little of a step up to be worth the effort. It's only a 48 megahertz microcontroller and didn't bring that much to the table. I think the only two things that it really added from memory were either built-in CAN or built-in USB. But you couldn't get a chip that had both of those, if my memory serves. So it was kind of, it's a small step forward, but not a big step forward. And if you're going to bother doing something new, why not grab something like a Teensy that gives you both of those things already built in? ESP32 is a very, very different style of chip. It's not necessarily designed to work in the same way as a classic microcontroller. It was specifically built around being a Wi-Fi type Internet of Things type device. And when I looked at it, and this is going back a little way now, it doesn't have a huge array of timers like you get on these new Cortex M4 type based MCUs. And in fact, it only had a very small number of timers, simply because that wasn't its sole purpose. It wasn't designed to work like a traditional microcontroller with those sorts of things. So no, the ESP32 is not really a suitable one, unless I've missed something or something's changed there. Have I put out the schematic for the drop bear? No, I haven't. I think I mentioned this last week that I'll release that once the drop bear becomes final. I don't like releasing schematics and designs for pre-release boards, because people use them and run with them and scream when things don't work, and they go, yeah, I know they don't work, it's still in development. I really hate doing that. I've been burned by that in the past. It just seems like it's a really good way for people to throw throw shade at you, I guess, because they announce on a forum that this thing's garbage, and everybody gets an idea that it's garbage, even though it's pre-release and these things are still being worked through. So they will be released, but not until the board designs are final. Oh, RISC-V architecture possibility. Oh, I'm so excited by RISC-V. I haven't looked at it that much myself, but I really do want to at some point in the future. There's a couple of really cool things going on in the RISC-V space. It's almost the opposite of user-friendly though. So maybe we can look at something like that in the future. I'm super excited by RISC-V, but way down the track. That's 5-year plan type stuff, I think, if it ever happens at all. Is the rearm board compatible? It's not compatible. I've never looked at it in depth, Chris. I've seen that board out there, but never played with it, I'm afraid. So I can't really comment on that. Yeah, RISC-V is all sorts of cool. I know a few people who are in that industry doing those sorts of things, and yeah, my mind is blown by RISC-V and its possibilities around that. So yeah, that's a huge one, but it's also a massive amount of work. Okay, I think I've managed to cover off most of the questions in here. So look, we might end up finishing up there for now. We've gone our usual traditional 15 minutes over time, but I think I've covered what I wanted to cover in terms of what the different considerations are for these microcontrollers, why I've gone a certain direction, and why I haven't gone in other directions, perhaps, is a good way of putting that. So I hope that gives everyone a reasonable idea for what my thinking is, but also what options are out there in terms of different microcontroller world. Okay, guys, we might wrap it up there for the week. Really appreciate you coming along, as always. I love having you guys come on. I love doing these sessions, and look forward to whatever I put up for next week. Thanks, guys.